Now, let's look at this particular aspect of the portfolio where I compute the variance and come out with efficient portfolio. How do I really, what is the process for creating an efficient portfolio or computing an efficient portfolio, and how do I get into the diversification of specific risk? Let's look at this example to consider the same. Consider a market which is having n securities, right? Now xi, let it denote the weight of the security I in a portfolio. So xi is the weight of security I in a portfolio. Vi is the variance of the security I, variance of the return of the security I, and Cij is the covariance between the returns on security I and security J. So we have a few letters to be used: Xi, Vi and Cij. These are the things that we are using. Write down the expression for V, the variance of return of the portfolio. So we know that now the portfolio is like something like this. If I'm talking about securities A and B as my portfolio, then it is like I have invested Xi here, XA here, and XB here, right? So the expected return has to be the expected return like this, whereas variance of this return XA times the return of A plus XB times the return of B. If I really want the variance like this, I'm more talking about XA squared times the variance of A plus XB squared times the variance of B plus twice XA XB times the covariance between A and B. This is what is the formula that we had. So the same logic, if I have to take it to multiple, if I want n number of securities being there, the variance of the portfolio will become for each of the weighted squares multiplied by their variance, means it is sigma xi squared multiplied by the variance of the ith securities. So for each security I am taking the variance, multiplying it with the weight squared. Along with that, 2xaxb can very well be written as xaxb times covariance AB. Along with that, I can also write it as xbxa times the covariance AB, and I am adding up those two. That's the reason the 2xaxb is coming up. The same logic, if I put, it is like xi, right, sigma xi xj, wherein across all values of I and all values of j, I am taking all the combination, and that has to be multiplied with the covariance between I and j. So here when I am taking all I and j's, they are not equal. So these two are non-equal kind, because when they are equal, it is becoming xi squared. So I don't need to consider the scenario when they are equal. The covariance is also becoming variance. That is what will translate into this. So the variance of the portfolio comes out like this. Now we are saying, describe how the efficient portfolio can be found here. So this is the variance of the portfolio. Now I have to create a scenario wherein I have to go with the minimum variance for a specific. So I need to really find out when this is my variance, sigma xi squared vi, plus sigma across I and j xi xj covariance of ij. When I have this as my variance formula, if I have to find out an efficient portfolio, the objective is I have to first determine these xi's in such a way that the overall variance is becoming as much minimum as possible. But at the same time, I have some constraints. The summation of all the weights should be equal to 1, and the expected return of the portfolio should be equivalent to whatever the expected return that I am looking at. So the E, whatever is the return that the portfolio is giving, which is nothing but sigma xi ri, the return on each asset. So this one should be equivalent to the expected return for my portfolio, whatever is the required expectation. So that is what are my constraints. So I have to minimize the variance, but I am subjected to two constraints. One, the summation of all these should be equal to 1, and the return wise I have a constraint that it should be equivalent to whatever I am specifying as my portfolio return. So if I have to solve this expression, I need to use Lagrangian multipliers. I can take the scenario when there are 2 or 3 securities, so that you can understand the things more easily. So let me take the scenario of 2 or 3 securities. So even if I go with 3, let's take this. The variance is x1 squared v1 plus x2 squared v2 plus x3 squared v3 plus 2x1 x2 covariance 1 and 2 plus 2x1 x3 covariance 1 and 3 plus 2x2 x3 covariance 2 and 3. So this is what I wanted to minimize by subjecting them to these constraints. So I have this constraint with respect to mu. So I'll say minus mu times, so E minus EP. So I'm all the constraints. So I will be taking them with some kind of parameter, mu times E minus mu P. Again the same logic I'll put here, minus lambda times x1 plus x2 plus x3 minus 1. Now even the expected return, I could have taken x1 R1 plus x2 R2 plus x3 R3. Those are the expected return. So minus EP. Now let's, if I have to really solve this expression, so I want to minimize this particular variance function by taking, so the way I will minimize it is, I'll go with the partial derivatives. So I'll take dou v by dou x1, dou v by dou x2, dou v by dou x3. Similarly, I'll take dou v by dou mu, and I'll also take the derivative with respect to lambda. Right? So these are the various derivatives that I'm going to take and equate all of them to 0. All 5 parameters, I'll take the derivatives and equate them to 0, which means if I just want to demonstrate with 1, so here if I'm looking at x1, it becomes 2x1 v1. Here no x1 term, here no x1 term. Here if I'm looking at, it is 2x2 c12 plus 2x3 C13, and if I'm looking at still a few more x1s, so it is coming out here as minus mu r1 minus lambda is equal to 0. So like this I get 5 equations. I'm not going to solve this here. I'm going to get 5 equations like this. 5 linear equations in 5 different variables. Now this is what 5 linear equations in 5 different variables. I can solve those linear equations and I can very well arrive at the values of x1, x2, x3, mu and lambda. So that is what will give me the solution based on what I get as a part of x1, x2, x3. That is the one I can very well take them as the weights associated with the minimum variance portfolio. Now, once I have got the values of the minimum variance kind of stuff where the variance is minimum, I've got values of x1, x2, x3 where the overall portfolio will have a minimum variance. Similarly, what I can do is I can try out all the combinations. So for each combination I will get the standard deviation or the variance of the portfolio. I will also consider the expected return of that portfolio. So the expected return is typically coming out as xi ri sigma. So by changing the different weights, I am getting the different expected returns of the portfolio. Even the variance of the portfolio is coming out as xi squared vi plus sigma across I and j xi xj cij. So based on these and taking the square root, I am getting the standard deviation, I am getting the expected value. Generally it is found that the graph is going to come something like this. When I am trying to plot the minimum standard deviation versus the expected value, so like this a kind of curve is going to come, and this is what we are calling as the portfolio frontier. But if you see here, let's say take this particular point, this is the standard deviation. But for this standard deviation, even this much return is possible or even this return is also possible. Obviously, for one single standard deviation, we are having two different portfolios, one of which is giving a lesser expected return, whereas the other one is giving a higher expected return. Which means all these portfolios which are giving lesser expected return for the same amount of risk are becoming inefficient portfolios. And at the same time, this one, the one that is giving me the least possible risk. So this is what we are calling as global minimum variance portfolio. Overall, this is the minimum amount of risk that I can get by investing in this portfolio. I cannot reduce the risk by any extent below this. So that is why I am calling it as a global minimum variance portfolio. So what you could see is the whole frontier, portfolio frontier, which is below this global minimum variance portfolio, results in portfolios which are inefficient, means they carry a higher risk which is measured in terms of standard deviation, but they are giving lesser expected returns. So obviously those portfolios will not be chosen for investment by any of the investors. So they are all inefficient portfolios, and that portion of this portfolio frontier which is above the global minimum variance means as the risk is increasing, as the standard deviation is increasing, the expected return of that portfolio is also increasing, which is very much supporting the fact that higher risk is resulting in higher expected return. So this portion of the curve which is above the global minimum variance portfolio, this portion of the curve which is above that is what is being typically called as the efficient frontier. That particular part of the curve which is above the global minimum variance portfolio is what we call efficient frontier. All the portfolios which are lying on that efficient frontier are typically considered to be efficient. So that's the important fundamental that we need to be aware of. So we can very well find the efficient portfolio, where one point we need to identify there is what is the global minimum variance portfolio, which we can very well find out using the Lagrangian multipliers. And once I draw a curve, all those portfolios which are above that global minimum variance portfolio, typically called as my efficient frontier, all the portfolios that are lying on that efficient frontier are considered to be efficient, all others are considered to be inefficient. Now, this is an interesting part. Show that the investor can diversify away a specific risk by investing equal amounts in an increasing number of independent securities. So the covariance or the correlation between them is zero. If the correlation is zero, covariance is zero. So obviously, when I am talking about the variance, sigma xi squared vi plus sigma xi xj cij. Xi xj cij, this is the total variance. Now we are saying that if they are independent, Cij will be 0. So the overall variance of the portfolio will be only this much. And now that I have n different securities, and if I am investing equal amounts, so which means the weightage in each one of them is 1 by n. So the same thing, if I look at it here, it becomes 1 by n squared Vi. And if I take out one n outside and then put Vi by n, so which is nothing but the summation by the total number, which is giving me the V bar, which is the average variance divided by n. So that is the variance of the portfolio. So I'll take the average variance divided by the number of securities, that will give me the variance of the portfolio. But here there is another line that is being specified, which is increasing number, which means as n is tending to infinite. So I see that this value will tend to 0. So which means the variance of the portfolio is going approximately equal to 0. So when the variance is going approximately equal to 0, I am able to diversify away the specific risk altogether. Or no risk is existing if I am investing equal proportions across the n different securities, provided all n of them are independent. It looks like I have diversified almost. My overall risk of the portfolio is very much approaching close to 0. So that is the kind of a property when the securities are independent. But now the question says, show that the result above still holds true when the securities are correlated, which means even if they are not independent, I want to see if I can diversify away the specific risk of the securities. Let's look at it. Xi squared Vi plus sigma xi xj cij. right? Now we know that because there are n securities, the weightage in each one of them is exactly 1 by n. So I will take it as 1 by n squared Vi plus sigma xi is 1 by n, xj is also the weightage is 1 by n, Cij. Now just some small calculation, I'll take one n out, making this part Vi by n, whereas here I will take n minus 1 by n out. So making this, if I am taking one n out and even n minus n, so this is becoming 1 by n into n minus 1 in the denominator and Cij. So Cij is talking about the pairwise, Cij is talking about the pairwise correlations that are existing between the assets, right? So we typically find out how manyCijs are there and C2 Cijs are there, which is n into n minus 1 by 2 Cijs are there altogether. And now if I am taking it the other way as well, because I did not do a 2 into, so if I am looking at number of permutations without the order, it is n into n minus 1. np2 Cijs are there. So which means I can very well look at this expression as 1 by n times. This I can take it as average variance, which I take it with V bar, and this I'll take it as n minus 1 by n times. This I'll take it as average covariance, because like this we have n into n minus 1 covariances that we are representing, and when I am dividing the same by n into n minus 1, I can very well take it as the average covariance across. So this is coming out as the average covariance. So overall it is coming out, the variance of the portfolio is coming out as 1 by n times average variance plus n minus 1 by n times average covariance. Now again, as n is going very large, tending to infinity, 1 by n tends to 0, so the overall variance is coming out to be 0, whereas here this will tend to 1. As n is tending to infinity, n minus 1 is coming closer to 1. So overall it is average covariance. So the overall variance approaches average covariance, but let's understand here, the average covariance is nothing to do with the specific risk. It's more and more associated with the interaction risk between the two securities. So still I am able to diversify away the specific risk by investing in an equal proportion across all the securities, provided the number of securities in which I am investing is pretty large. So that's how we can evaluate the various calculations associated with the portfolio. Whether it is equal variance or whether there is a correlation or there is no correlation, as long as I am able to invest equal amounts into the portfolio for all the securities, more or less I am diversifying the specific risk in total. All that would be left with is the average correlation across the various securities. That could be the total overall variance of the portfolio, right?